Good afternoon, ladies and gentlemen of Algebra 2 Honors. Good to have everybody here today. We're just missing 2 volleyball players, so they're going to be caught up. So I want to go over some of these problems pretty quickly. We're probably not going to get through all these, but I don't know how you did this. The way I looked at it, and you can correct me if I'm wrong, or if you have another suggestion, that's fine. But the way I like to do this is sort of look at a distributive property like this. I don't know if you look at that, and then just kind of rewrite like 4 minus, and then we have negative 3 times 2, so that's going to be minus 6x, and then negative 3 times negative 5 is 15, so I'll put plus 15, and that's going to be equal to 6x minus 7. And then combining like terms, so we got 19 minus 6x equals 6x minus 7. Does that look okay so far? Okay, and then if I'm gonna try to solve for this side over here, for x over here. So what I'm going to do is I'm going to add 6x to both sides here, like this. And then I'm going to get rid of the 7 by adding it here and adding it here. And so that goes away and that goes away. So I get 6x plus 6x, which is 12x, is equal to 26. And I'm kind of I don't know, this is kind of a technique that I like to use. I'm sort of in the habit when I'm solving for something, I like to put that x over there on the left side. Now you can keep it on the right side if you want to, Michelle, you can do that. But that's just sort of what happens, I get into these habits or procedures that give me a more uniform look at the way to solve the problem. So that's the way I look at things. Then if you divide out by 12, you have x is equal to, you can like simplify the fraction, and so you get like 13 over 6 would be your most simplified fraction of that. Does that look right?
Yeah,
okay.
That's legit.
Okay, good.
I mean, I did it in decimal form, and I just got 6 repeating, so I can definitely say that's true.
So you got a decimalized form? Yeah.
Yeah, it's 6 repeating, so that's...
Yeah.
So that...
And then the next one we have here is this one, solving inequalities problem. And so for this one, it's really quite similar to the last one, isn't it? And I have this, I'm going to go ahead and subtract 4x like this. And then I'm going to add 7 like this. And once I do that, what we have on the left side, I got 12 is less than 2x. Does that look right? And then again, because of the way I like to solve things, I'm going to just rewrite this as 2x is less than 12. Oh, excuse me, I got it wrong, don't I? 2x is greater than 12. Is that right? 2x is greater than 12. Thank you. And what happens is I had problems with inequality when I was in high school. I asked my teacher, how do you get this greater than less than thing right? He says, well, it's really pretty easy if you consider that like the arrow is always pointing to the smaller number. Okay, so that helps me look at it. And then if you divide by 2, you get x is greater than 6. And then the last thing it says solve, show your answer graphically with set builder and interval notation. Well, greater than 6 to solve graphically, when they say that can be a number line at x equals 6. And if you're greater than 6, that's going to look something like this. Okay, does that make sense? So that's your graphing on a number line. And then your set notation. What you have, set notation is something you may not be familiar with. It looks like this, x such that x is greater than 6. That's called set notation. And finally, you have interval notation. And by the way, this thing down here, it's called inequality notation. And then interval notation Now, interval notation is eventually where we're headed. You get to more advanced mathematics, that's the most popular thing. And what that is, that's made out of parentheses and commas and infinity symbols, negative infinity. So in this case, what we have is, this means greater than 6, comma, less than infinity. So this is what interval notation looks like. You see how compact and efficient that is, the interval notation? And you're going to get pretty familiar with it. Anybody seen interval notation before? That's going to be the big thing. You guys that are going on to more advanced mathematics, that's going to be your go-to at a time. But we're going to spend a lot of time in this class in using set notation too. But this interval notation, that's where we're headed. Okay. Next, we have this one here, evaluate expressions. So evaluating expressions is basically plugging in for x. So any place I see x, I'm going to replace that with a 4. And I put minus 2 times 3 minus 4. And then I'm going to replace this x with 4. And then we just use order of operations to simplify where we can. And so we have 3 times 4, which is 12. And then we have minus 2 times, and then we're going to simplify all this within these parentheses here. So we have 3 minus 16. What's 3 minus 16? Negative 13, right? And so now what we have is we have 12, and we have minus times minus, so that's going to be plus 26. And so our answer is going to be 38, right? Okay? It makes sense? People have too much trouble with, shouldn't have too much trouble with this, right? Yeah. Okay. PV equals nRT. Has anybody taken chemistry yet? You have, right? Anybody remember this? Boyles Law? This is Boyles Law. PV equals nRT. And so you're solving for T. And I've actually used this equation in my engineering profession, by the way. So anyway, I'm going to solve for T. And so we're going to divide by NR. And so these will cancel out here. So you get T is equal to PV over NR. Yeah, we had these big propane tanks, and we were trying to figure out how much of this propylene gas these tanks could hold. So we used this equation for that. Boyles Law. Okay, questions on this? Okay, domain and range. Determine if the relation is a function, find the domain and range. We had some interesting discussion over this problem in period 6. Is this thing here a function?
No.
Okay, Ashton, he sounded really confident about that. Okay, he says no. Okay, he's right. Why is he right?
Because x is repeating.
Yeah, x is repeating. Thank you, Kimberly. Very good. Yeah, this thing right here, if there are 2 y's for an x, it's not a function. One thing depends on another. So that tells you it is not a function. Thank you. Okay, and what is our domain for this?
-1, 0, and 1.
Yeah, now, one thing, I had somebody in 6th period who said, first of all, well, what that's going to be is greater than or equal to -1, less than or equal to 1. But why is this thing here not right?
Because it has to be -2.
Oh, okay, yeah, I meant to put this, hang on a second. Well, actually, for the domain, yeah, This would be right for the domain except what? Okay, the problem with this one here is this represents continuous data. So this thing here would contain not only -1, but -0.9, -0.8, and all this. So this is what's called continuous data, but really what we have is discrete data, which means only these numbers. So only -1, only 0, and only 1. So this is a case when set notation is pretty helpful in figuring that out. You remember that too from class, don't you? From this? Yeah. Okay, in range, same sort of thing, right? So again, it's called discrete data. And basically anything you can measure and data-wise is continuous, like the air temperature in this room, how much a person weighs, anything that is measurable like that, that's continuous data. In this case, we have discrete data. Okay, this one right here, footballs cost $22 each. The athletic director has $277. So this is the maximum we can spend, and that's going to have to be greater than or equal to our $13 shipping fee plus our 22 N. We'll call it N for numbers of football. And then if we subtract out 13, we get 264 is greater than or equal to 22N plus 13. And then if we, oops, I already subtracted 13, right? Sorry about that. So we have that. So if we divide by 22, we get, what is that going to be? 12, right? So N has to be less than or equal to 12. So that's the number of footballs, the maximum number of footballs we can get, right? Okay? And so that's it. And that's as far as I want to go today. What I want to do is I want to finish the class by our Algebra 2 song. We have a song this year. And we won't get through the whole thing. Not enough of it to, you keep that paper for tomorrow, okay? A long, long time ago, I once had a teacher who taught me how to wrap a line. You remember the song, don't you?
Not really.
Don't remember? You should remember. But now over a year has passed, and my mind is full of mass with summer memories that are the past. But now I'm back in school session, and I've got a sad confession. My skills, draws of one-step, fraction, a lost concept. Algebra 1 has been so long, and that's why my teacher sang this song. Because when he saw my work, it was all wrong. So that's why I'm going to sing this song. Where do I start? I'm trying to why I intersect, and things will be fun. I need to find my points one, so I use the slope as rise over run. The slope is rise over run. Now that we use the slope, it's rise over run. It's the M in front of X. Look at that on top and use it to move up and stop. Almost done, but there's one more hop. Now use the run and move to the right. Draw your dot. Are we done? Not quite. Draw the lines you can make the dots. So draw arrows because lines never stop. Now I think I can rest, but I remember the process. But I always check my work because I might be wrong. So for now, I'm going to sing this song. Anyway, there's a little more to it. That's most of it. See you tomorrow. Thank you. See you tomorrow.
I told you.
You know what?